Imagine standing beneath a starlit sky, watching the gentle glow of distant galaxies, painting the darkness with their ancient light. Each photon that reaches your eyes has traveled for millions, perhaps billions of years, racing through the cosmic void at a speed so fundamental that it defines the very nature of our universe. This speed, approximately 299,792,000 kilometers per second in the vacuum of space, is what we call the speed of light. But tonight we invite you to embark on a journey of imagination and wonder. What would happen if this cosmic constant, this seemingly unchangeable pillar of physics, were to slow down? What if the speed of light, which has remained steady since the birth of the universe 14 billion years ago, suddenly began to decrease? The speed of light is not merely a number in a physics textbook. It is the heartbeat of the cosmos, the rhythm by which space and time dance together in perfect harmony. It determines how quickly information can travel across the universe, how gravity bends space around massive objects, and even how we experience the passage of time itself. Every law of physics, every equation that describes our reality depends on this one fundamental constant. Picture the light from our sun taking 8 minutes and 20 seconds to reach Earth. Imagine the signals from distant pulsars, those cosmic lighthouses spinning in the depths of space, their beams sweeping across the galaxy like clockwork. Consider the delicate dance of electrons around atomic nuclei, governed by the same forces that give light its speed. All of these phenomena, from the grandest cosmic structures to the tiniest quantum interactions, are intimately connected to the speed of light. Yet what if this speed were not constant? What if it could change, slow down, or vary across different regions of space and time? The implications would be profound, touching every aspect of our understanding of reality. Time itself might flow differently. Gravity could behave in unexpected ways. The very atoms that make up our bodies might respond to new rules of physics. As we begin this exploration, let your mind wander to the possibilities that await us. We will journey through the consequences of a slower speed of light, examining how it would affect everything from the expansion of the universe to the quantum realm that exists beneath our everyday experience. We will discover how such a change might alter the fundamental forces of nature, reshape the cosmos itself, and challenge our deepest assumptions about the nature of reality. So close your eyes and imagine a universe where light moves more slowly, where the cosmic speed limit has been reduced, and where the very fabric of space and time responds to this change in ways both subtle and dramatic. This is not just a thought experiment, but an invitation to understand how deeply interconnected all things are in our magnificent, mysterious universe. Tonight, we explore the profound question that has captivated physicists and philosophers alike. What would happen if the speed of light were to slow down? The answer, as we shall see, touches the very heart of existence itself. To truly understand what would happen if the speed of light slowed down, we must first appreciate the remarkable role this cosmic constant plays in our universe. The speed of light in a vacuum is precisely 299,792,458 meters per second. This number might seem arbitrary, but it represents one of the most fundamental properties of our reality. Light does not simply illuminate our world, it is the messenger that carries information across the cosmos, the thread that weaves space and time together, and the ultimate speed limit that governs every interaction in the universe. When you look up at the night sky, you are not seeing the stars as they are now, but as they were when their light began its journey towards Earth. The nearest star beyond our Sun, Proxima Centauri, appears to us as it was 4 years and 4 months ago, because that is how long its light takes to reach us. This delay is not merely an inconvenience. It is a fundamental feature of how our universe operates. Nothing can travel faster than light, not matter, not energy, not even information itself. This speed limit is built into the very structure of space and time, creating what physicists call the light cone, a boundary that separates the events that can influence each other from those that cannot. Consider the profound implications of this cosmic speed limit. When major events occur in distant parts of our galaxy, such as the explosion of a massive star in a supernova, the light from that event must travel for thousands or even millions of years before it reaches us. During all that time, the information about what happened remains locked away, unable to affect anything in our local region of space. The universe is filled with countless events that have already occurred, but whose effects have not yet reached us, creating a complex tapestry of cause and effect stretched across space and time. The Andromeda Galaxy, our nearest major galactic neighbor, is approximately 2.5 million light-years away. When we observe it through our telescopes, we are seeing it as it existed when our early human ancestors were just beginning to walk upright on the African savanna. The light that left Andromeda when the first stone tools were being crafted is only now reaching our eyes. This cosmic time delay means that the universe is filled with a rich history of events, each one locked in time until its light finally reaches us. The speed of light also determines how we measure distances in the cosmos. When astronomers speak of objects being millions of light-years away, they are using light itself as a cosmic ruler. A light-year is the distance that light travels in 1 year, approximately 9,461,000,000,000 kilometers. This unit of measurement reminds us that in the vast expanses of space, distance and time become intimately connected. To look far into space is to look far back in time. But light's role extends far beyond simply carrying information across the universe. It is also the mediator of one of the 4 fundamental forces of nature, the electromagnetic force. Every time electrons interact with each other, every time atoms bond together to form molecules, every time your neurons fire to create a thought, these interactions are mediated by particles of light called photons. These photons carry the electromagnetic force at exactly the speed of light, making this cosmic constant essential to every chemical reaction and every biological process. The electromagnetic force is responsible for the structure of matter itself. It holds electrons in their orbits around atomic nuclei, binds atoms together into molecules, and creates the chemical bonds that make life possible. The strength of this force depends precisely on the speed of light, woven into the very equations that describe how charged particles interact with each other. This means that the speed of light is not just about light itself, but about the fundamental forces that shape the material world. Consider the delicate dance of electrons around the nucleus of a hydrogen atom, the simplest and most abundant element in the universe. The electron orbits at precisely the right distance from the proton, creating a stable atom that can exist for billions of years. This stability depends on the balance between the electromagnetic force pulling the electron toward the nucleus and the quantum mechanical properties that keep it in motion. Both of these phenomena are intimately connected to the speed of light. The speed of light also plays a crucial role in determining the strength of the electromagnetic force itself. If light moved more slowly, the electromagnetic interactions between particles would be different, potentially altering the stability of atoms, the behavior of molecules, and even the possibility of life as we know it. The delicate balance that allows electrons to orbit atomic nuclei at precisely the right distances depends on the speed at which electromagnetic forces can propagate. In the realm of modern technology, the speed of light sets the ultimate limit on how quickly our devices can communicate with each other. The signals in our computers, the data flowing through fiber optic cables, and the radio waves carrying our phone calls all travel at the speed of light. This creates fundamental constraints on how fast our technology can operate and how quickly information can be processed. When you send a message to someone on the other side of the world, that information travels through cables and satellites at the speed of light. Even though this seems instantaneous to us, there is always a tiny delay as the signal makes its journey. For communication between Earth and spacecraft exploring the outer planets, these delays become very noticeable. A signal sent to the Voyager spacecraft, now beyond the edge of our solar system, takes over 22 hours to reach its destination. The speed of light also determines how quickly computer processors can operate. The fastest supercomputers in the world are limited by how quickly electrical signals can travel between different parts of the machine. As computer chips become smaller and more complex, engineers must carefully consider the speed of light when designing circuits and connections. Even our understanding of simultaneity, the concept of events happening at the same time, depends on the speed of light. What we consider to be simultaneous depends on our reference frame and how quickly information can travel between different locations. This relativity of simultaneity, first recognized by Albert Einstein, shows us that the speed of light is not just a property of light itself, but a fundamental feature of the structure of space and time. This means that the speed of light affects our very perception of reality. Two events that appear simultaneous to one observer might not be simultaneous to another observer moving at a different speed. This strange property of time is not just a theoretical curiosity, it has practical implications for technologies like GPS satellites, which must account for these relativistic effects to provide accurate positioning information. The speed of light also influences the behavior of matter at the smallest scales. In the quantum world, particles can exist in multiple states simultaneously, a phenomenon known as superposition. When these quantum systems are measured or observed, they collapse into definite states, and this collapse happens at speeds related to the fundamental constants of nature, including the speed of light. Quantum entanglement, one of the most mysterious phenomena in physics, also relates to the speed of light. When two particles become entangled, measuring one instantly affects the other, regardless of the distance between them. This seems to violate the speed of light limit, but it does not actually allow information to travel faster than light. Instead, it reveals the deep interconnectedness of the quantum world and the subtle ways in which the speed of light influences even the strangest aspects of reality. As we contemplate what would happen if this cosmic constant were to change, we begin to see that the speed of light is not merely the speed at which light travels. It is a fundamental parameter that governs the behavior of space, time, matter, and energy. It determines how quickly causes can produce effects, how forces can act across distances, and how the universe can maintain the delicate balance that makes complexity and life possible. The speed of light appears in the equations that describe the conversion of matter into energy, famously expressed in Einstein's equation E equals mc squared. This relationship tells us that even a small amount of matter contains an enormous amount of energy, and this energy is released when matter is converted in processes like nuclear fusion in stars. The speed of light squared appears in this equation, showing how this cosmic constant is woven into the very fabric of matter and energy. The speed of light is truly the heartbeat of the cosmos, and any change to this fundamental rhythm would send ripples through every aspect of our reality. From the largest galaxies to the smallest quantum particles, from the flow of time to the structure of space, everything in our universe is connected to this one fundamental constant. Light is not just fast. It is the key to our understanding of reality itself. But if that speed were to change, how would everything we know be affected? In the early years of the 20th century, a young patent clerk named Albert Einstein was pondering one of the most fundamental questions about our universe. What would it be like to ride alongside a beam of light? This simple thought experiment led to one of the most revolutionary discoveries in the history of science, forever changing our understanding of space, time, and the speed of light itself. Einstein's theory of special relativity, published in 1905, revealed that the speed of light is not just another speed among many. It is the fundamental speed limit of the universe, a cosmic constant that remains the same for all observers, regardless of how fast they are moving. This discovery overturns centuries of assumptions about the nature of space and time, showing that these seemingly separate concepts are actually woven together into a single fabric called space-time. The journey to this understanding began with a puzzle that had been troubling physicists for decades. Light behaves as both a wave and a particle, and waves typically require a medium through which to travel. Ocean waves travel through water. Sound waves travel through air. So scientists naturally assumed that light waves must travel through some invisible substance that fills all of space. They called this hypothetical medium the luminiferous ether. But when scientists tried to detect this ether, they found nothing. The famous Michelson-Morley experiment of 1887 attempted to measure Earth's motion through the ether by comparing the speed of light in different directions. If the ether existed, light should travel faster in some directions than others as Earth moved through this cosmic medium. But the experiment found that light travels at exactly the same speed in all directions, regardless of Earth's motion. This result was deeply puzzling until Einstein proposed a radical solution. What if there is no ether? What if light simply travels through empty space at a constant speed, and this speed is the same for all observers? This idea seemed impossible at first, because it challenged our everyday understanding of motion. If you are riding in a car and throw a ball forward, the ball's speed relative to the ground is your speed, plus the ball's speed. But Einstein proposed that light does not follow this simple rule. According to special relativity, if you shine a flashlight while traveling at high speed, the light from that flashlight will still travel at exactly the same speed as light from a stationary flashlight. This seems to violate common sense, but it has been confirmed by countless experiments and is now one of the most thoroughly tested principles in physics. This constant speed of light leads to some truly remarkable consequences. As objects approach the speed of light, time begins to slow down from the perspective of a stationary observer. This phenomenon, called time dilation, means that a clock moving at high speed will tick more slowly than a stationary clock. The faster you go, the more pronounced this effect becomes. At 90% the speed of light, time would pass about twice as slowly for the moving observer. Length contraction is another strange consequence of relativity. Objects moving at high speeds appear shorter in the direction of their motion. A spacecraft traveling at 90% the speed of light would appear to be compressed to less than half its original length. These effects are not optical illusions, but real changes in the structure of space and time itself. The most famous consequence of special relativity is perhaps the relationship between mass and energy, expressed in the equation E equals mc squared. This equation tells us that mass and energy are different forms of the same thing, and that even a tiny amount of mass contains an enormous amount of energy. The c in this equation represents the speed of light, and the fact that it is squared shows just how much energy is locked away in matter. This mass-energy equivalence explains how stars shine. In the core of our sun, hydrogen nuclei fuse together to form helium, and a small amount of mass is converted into energy in the process. The energy released in this fusion travels outward from the sun's core, eventually reaching the surface and radiating into space as sunlight. The light that warms our planet and makes life possible is a direct manifestation of Einstein's famous equation. But why is the speed of light the ultimate speed limit? The answer lies in the way that energy and momentum behave at high speeds. As an object with mass accelerates toward the speed of light, its energy increases without limit. To actually reach the speed of light would require infinite energy, which is impossible. Only massless particles, like photons, can travel at the speed of light. This speed limit has profound implications for space travel. Even with the most advanced propulsion systems we can imagine, it would take enormous amounts of energy to accelerate a spacecraft to even a small fraction of the speed of light. The nearest star system, Alpha Centauri, is over 4 light-years away. With current technology, it would take tens of thousands of years to reach it, even with a spacecraft that could travel at 10% the speed of light. The journey would still take over 40 years. The speed of light also determines the structure of space-time itself. Einstein's general theory of relativity, published in 1915, extended special relativity to include gravity. In this theory, massive objects like stars and planets create curves in the fabric of space-time, and these curves are what we experience as gravitational force. The speed of light appears throughout the equations of general relativity, showing that this cosmic constant is fundamental to the geometry of space and time. One of the most striking predictions of general relativity is that gravity affects the flow of time. Clocks run slightly slower in stronger gravitational fields, an effect called gravitational time dilation. This means that time passes more slowly on the surface of Earth than it does in the empty space far from any massive objects. The effect is tiny, but it is real and measurable. GPS satellites must account for this effect to provide accurate positioning information. General relativity also predicts that massive accelerating objects should create ripples in space-time called gravitational waves. These waves travel at exactly the speed of light, carrying energy away from their source. For decades, gravitational waves remained purely theoretical, but in 2015, scientists finally detected them using incredibly sensitive instruments called LIGO detectors. These waves were created by the collision of 2 black holes over 1 billion light-years away, and they traveled across the universe at the speed of light before reaching Earth. The detection of gravitational waves opened up an entirely new way of studying the universe. Just as visible light, radio waves, and X-rays each reveal different aspects of cosmic phenomena, gravitational waves allow us to observe events that would be invisible to traditional telescopes. They provide direct evidence that space-time is indeed a dynamic, flexible medium that can be stretched and compressed by the motion of matter and energy. Black holes represent perhaps the most extreme consequence of relativity. These objects are so dense that they create such deep curves in space-time that nothing, not even light itself, can escape once it crosses the event horizon. The event horizon is defined by the speed of light. It is the boundary where the escape velocity equals the speed of light, making it impossible for anything to return to the outside universe. Near a black hole, the effects of relativity become dramatically apparent. Time dilation becomes so extreme that an outside observer would see time slow to a crawl for anything approaching the event horizon. Length contraction would stretch objects into long, thin shapes in a process called spaghettification. These effects are not just theoretical curiosities, but real physical phenomena that govern the behavior of matter and energy in the most extreme environments in the universe. The speed of light also plays a crucial role in determining the fate of information that falls into a black hole. According to current understanding, information cannot be destroyed, but it also cannot escape from inside a black hole. This creates a paradox that physicists are still working to resolve. The solution to this puzzle may require new insights into the relationship between quantum mechanics and relativity, two theories that both depend fundamentally on the speed of light. Einstein's theories also predict that space itself can expand faster than the speed of light. This might seem to violate the cosmic speed limit, but it does not. The speed limit applies to objects moving through space, not to the expansion of space itself. In the early moments after the Big Bang, space expanded so rapidly that distant regions of the universe were carried apart faster than light could travel between them. This period, called cosmic inflation, explains many features of the universe we observe today. The cosmic microwave background radiation, the afterglow of the Big Bang, provides evidence for this rapid expansion. This radiation has been traveling toward us for nearly 14 billion years, carrying information about the state of the universe when it was only 380,000 years old. The patterns in this radiation tell us about the density fluctuations that eventually grew into galaxies and stars, all governed by the fundamental role of the speed of light in shaping space-time. As we contemplate what would happen if the speed of light were to slow down, we must remember that this constant is not just a property of light itself. It is woven into the very fabric of space-time, determining how space and time relate to each other, how gravity works, and how information can flow through the universe. A change in the speed of light would not simply mean that light travels more slowly. It would mean that the fundamental structure of reality itself would be altered. Einstein's theories tell us that light's speed defines the very nature of time and space. But what if that constant speed were to change? Imagine for a moment that you could slow down the speed of light with a cosmic dimmer switch. As you gradually reduce this fundamental constant, the very fabric of space and time would begin to respond in ways both subtle and profound. The universe would not simply become a darker place. Instead, the basic relationship between space and time, the foundation upon which all physical reality rests, would shift beneath our feet like sand dunes in a cosmic wind. To understand how slowing light would affect time and space, we must first appreciate how intimately these concepts are connected to light's speed. In Einstein's universe, space and time are not separate entities, but different aspects of a single four-dimensional continuum called space-time. The speed of light serves as the conversion factor between space and time, much like how an exchange rate converts between different currencies. Change the speed of light, and you change the fundamental relationship between these two most basic dimensions of existence. Consider what happens when objects travel at high speeds in our current universe. As a spacecraft approaches the speed of light, time dilation occurs. Clocks aboard the spacecraft tick more slowly compared to clocks on Earth. An astronaut traveling at 99% the speed of light would experience time passing about 7 times more slowly than people on Earth. A journey that takes 1 year from the astronaut's perspective would correspond to 7 years passing on Earth. But what would happen if the speed of light itself was slower? The mathematics of relativity tells us that time dilation effects would become noticeable at much lower speeds. If the speed of light were reduced to just 30,000 kilometers per second, roughly 1/10 of its current value, then a car traveling at highway speeds would experience measurable time dilation. The driver would age slightly more slowly than passengers standing at the roadside. This change would fundamentally alter our everyday experience of motion and time. High-speed trains, jet aircraft, and even fast-moving cars would become time machines of sorts, carrying their passengers into a slightly different temporal reference frame. The synchronization of clocks across different locations would become a complex challenge, as the time difference between moving and stationary observers would no longer be negligible. Length contraction would also become apparent at everyday speeds. Objects moving at what we currently consider normal velocities would appear shortened in the direction of their motion. A train traveling at 300 kilometers per hour in a universe with slower light would appear noticeably compressed to observers on the platform. The train's passengers, however, would see the platform and everything on it as compressed instead. These effects would ripple through every aspect of our technological civilization. GPS satellites, which currently require corrections for relativistic effects that amount to microseconds per day, would need corrections measured in seconds or even minutes. The entire global positioning system would need to be completely redesigned to account for the much stronger relativistic effects in a slower light universe. But the changes would extend far beyond mere technological inconveniences. The very nature of simultaneity would be dramatically altered. In our current universe, events that appear simultaneous to different observers can be slightly out of sync, but this effect is only noticeable for observers moving at very high speeds. In a slower light universe, the relativity of simultaneity would become apparent in everyday situations. Imagine two people walking toward each other on a sidewalk. In our current universe, they would agree about the timing of distant events like the ringing of a church bell. But in a universe with slower light, their relative motion would cause them to disagree about when the bell rang. One person might hear it before seeing the bell tower's movement, while the other experiences these events in the opposite order. The very concept of now would become ambiguous and observer dependent in ways that would challenge our fundamental assumptions about reality. The structure of space-time itself would be different in a slower light universe. Einstein's equations tell us that space-time curvature, which we experience as gravity, depends on the speed of light. A slower speed of light would affect how mass and energy curve space-time, potentially altering the strength of gravitational effects. Massive objects like planets and stars might create deeper or shallower curves in space-time, changing the orbits of planets and the behavior of light rays passing near massive objects. This could have profound implications for the stability of planetary systems. The Earth's orbit around the Sun depends on a delicate balance between the Sun's gravitational pull and the planet's orbital motion. If the speed of light were different, the mathematics of this orbital dance would change, potentially making our orbit more elliptical or even unstable over long time periods. The speed at which gravitational effects propagate would also change. Currently, if the Sun were to suddenly disappear, Earth would continue in its orbit for 8 minutes and 20 seconds, the time it takes light to travel from the Sun to Earth. This is because gravitational effects, like electromagnetic effects, propagate at the speed of light. In a slower light universe, gravitational changes would also propagate more slowly, creating a universe where cause and effect are more obviously separated in time. Consider the implications for binary star systems, where two stars orbit around their common center of mass. These cosmic dances are governed by the speed at which gravitational information can travel between the stars. In a slower light universe, the gravitational signals between the stars would be delayed, potentially making these systems less stable or causing them to evolve differently over cosmic time. The behavior of black holes would also be fundamentally altered. The event horizon of a black hole is defined as the distance from the center, where the escape velocity equals the speed of light. In a slower light universe, event horizons would be located closer to the centers of black holes, making these objects appear smaller but potentially more numerous, as less massive objects could form black holes. Time dilation near massive objects would also be affected. Currently, time passes more slowly in stronger gravitational fields, an effect that is proportional to the gravitational potential and inversely related to the speed of light squared. In a slower light universe, gravitational time dilation would be much stronger. Clocks at sea level would run noticeably slower than clocks on mountaintops, and the effect would be easily measurable with everyday instruments. This enhanced gravitational time dilation would create new challenges for maintaining synchronized time across different elevations. Skyscrapers would need to account for the time difference between their ground floors and upper stories. Air traffic control would need to consider how altitude affects the flow of time for aircraft at different flight levels. The relationship between energy and mass would also be transformed. Einstein's equation, E equals mc squared, shows that the energy content of matter depends on the speed of light squared. In a slower light universe, the energy locked away in matter would be dramatically reduced. Nuclear reactions would release less energy, making stars burn less brightly and for longer periods. The nuclear fusion that powers our sun would proceed more slowly, potentially extending the sun's lifetime but reducing its luminosity. This change in the mass-energy relationship would affect every process that involves the conversion between mass and energy. Radioactive decay would proceed differently, as the energy available for these processes would be reduced. The strong nuclear force that holds atomic nuclei together might be affected, potentially changing the stability of different elements and isotopes. Particle accelerators, which currently require enormous amounts of energy to accelerate particles to near light speed, would face different constraints in a slower light universe. The maximum energy that could be imparted to particles would be lower, but particles would reach higher fractions of the reduced light speed with less energy input. This could actually make some high-energy physics experiments easier to perform, while making others impossible. The cosmic speed limit would create new boundaries for space travel. While it might initially seem that slower light would make interstellar travel more difficult, the reality is more complex. The energy required to reach a given fraction of light speed would be unchanged, but that fraction would correspond to a lower absolute velocity. However, the time dilation effects would kick in at lower speeds, potentially making relativistic space travel accessible with less advanced technology. Quantum mechanics would also feel the effects of slower light. The uncertainty principle, which relates the uncertainty in position to the uncertainty in momentum, involves Planck's constant and the speed of light. Changes to light speed could alter the balance between quantum uncertainty and classical determinism, potentially making quantum effects more or less noticeable at macroscopic scales. The speed at which quantum information can be processed and transmitted would also change. Quantum entanglement, that mysterious connection between particles that seems to operate faster than light, would still be limited by the speed of light when it comes to actually transmitting usable information. In a slower light universe, quantum communication systems would operate more slowly, affecting everything from quantum computers to secure communication networks. Even the structure of atoms might be different. The fine structure constant, which determines the strength of electromagnetic interactions, depends on the speed of light. Changes to light speed could alter this constant, potentially affecting the energy levels of electrons in atoms and the wavelengths of light that atoms absorb and emit. This could change the colors of stars, the efficiency of photosynthesis, and the absorption properties of materials. As we contemplate these far-reaching changes, we begin to see that slowing the speed of light would not simply make the universe a bit dimmer or communication a bit slower. It would fundamentally alter the relationship between space and time, changing how we experience motion, how gravity works, and how energy and matter interact. The delicate balance of space and time depends on light, and slowing light could set off a chain reaction that alters our very understanding of reality. Gravity is perhaps the most familiar yet mysterious of all the fundamental forces. We experience it every moment of our lives as the gentle pull that keeps our feet on the ground and our planet in orbit around the sun. Yet gravity is also the force that shapes the largest structures in the universe, from the spiral arms of galaxies to the cosmic web of dark matter that spans billions of light years. What makes gravity truly remarkable is how intimately it is connected to the speed of light, and how dramatically it would change if that cosmic constant were to slow down. To understand how slower light would affect gravity, we must first appreciate that gravity is not simply a force pulling objects toward each other. According to Einstein's general theory of relativity, gravity is the curvature of space-time itself. Massive objects like stars and planets create dips and valleys in the fabric of space-time, much like a bowling ball creates a depression when placed on a stretched rubber sheet. Other objects then move along the curved paths created by this distortion, which we interpret as gravitational attraction. The speed of light appears throughout Einstein's field equations, which describe how mass and energy curve space-time. This cosmic constant determines not just how quickly gravitational effects propagate through space, but also how strong those effects are and how they influence the geometry of space-time itself. Change the speed of light, and you change the fundamental nature of gravity. In our current universe, gravitational effects propagate at exactly the speed of light. When massive objects accelerate or change their distribution of mass, they create ripples in space-time called gravitational waves that travel outward at light speed. If the Sun were to suddenly vanish, Earth would continue in its current orbit for 8 minutes and 20 seconds, the time it takes for the gravitational signal of the Sun's disappearance to reach us. This delay is not just a theoretical curiosity, but a fundamental feature of how information about changes in gravitational fields spreads throughout the universe. In a slower light universe, gravitational waves would propagate more slowly, creating a cosmos where cause and effect in gravitational systems are more obviously separated in time. Binary star systems, where two massive stars orbit around their common center of mass, would behave differently. The gravitational signals between the stars would be delayed, creating a lag between each star's motion and the gravitational field experienced by its companion. This delay could fundamentally alter the stability and evolution of such systems. Currently, binary stars lose energy by emitting gravitational waves, causing their orbits to gradually shrink as the stars spiral toward each other. In a slower light universe, this process might proceed differently, as the reduced speed of gravitational wave propagation could affect both the rate of energy loss and the dynamics of the orbital decay. The strength of gravitational effects would also be modified in a slower light universe. The gravitational field around a massive object depends on what physicists call the gravitational coupling constant, which is related to Newton's gravitational constant, but also involves the speed of light. Changes to light speed would alter this coupling, potentially making gravity stronger or weaker, depending on the specific mathematical relationships involved. Consider what this might mean for planetary orbits. The delicate balance that keeps Earth at just the right distance from the Sun depends on the precise strength of gravitational attraction. If gravity was stronger in a slower light universe, Earth might spiral inward toward the Sun. If gravity were weaker, our planet might drift outward into the cold depths of space. The habitable zone around stars, that narrow band of orbital distances where liquid water can exist on planetary surfaces, would shift accordingly. The formation of planetary systems would also be affected. When a new star system forms from a collapsing cloud of gas and dust, gravity plays the crucial role of pulling material together, while angular momentum creates the spinning disk from which planets eventually coalesce. In a slower light universe, the balance between gravitational collapse and rotational motion would be different, potentially leading to planetary systems with different architectures and characteristics. Black holes, those most extreme manifestations of gravity, would be profoundly affected by changes in the speed of light. The event horizon of a black hole is defined as the boundary where the escape velocity equals the speed of light. In a slower light universe, event horizons would be located closer to the centers of black holes, making these objects appear smaller from the outside. This change would have cascading effects throughout the universe. Stellar mass black holes, formed when massive stars collapse at the end of their lives, might be more common in a slower light universe if the reduced escape velocity made it easier for collapsing stars to form event horizons. Conversely, the supermassive black holes found at the centers of galaxies might behave differently, potentially affecting the formation and evolution of the galaxies themselves. The accretion disks of material spiraling into black holes would also be affected. As matter falls toward a black hole, it forms a hot, glowing disk that radiates enormous amounts of energy. The physics of these accretion disks depends on the interplay between gravity, electromagnetic forces, and relativistic effects, all of which involve the speed of light. In a slower light universe, accretion disks might be more or less efficient at converting matter into energy, changing the luminosity of quasars and other active galactic nuclei. Gravitational time dilation, the slowing of time in strong gravitational fields, would be dramatically enhanced in a slower light universe. This effect depends on the ratio of the gravitational potential to the speed of light squared. So reducing light speed would make time dilation much more pronounced. Near the surface of a neutron star, where gravitational fields are incredibly strong, time might pass hundreds or thousands of times more slowly than in empty space. This enhanced time dilation would create new challenges for any hypothetical civilization trying to communicate across different gravitational environments. Signals sent from the surface of a massive planet to a spacecraft in orbit would be severely redshifted, with the frequency of the signals reduced by the time dilation effect. Radio communications would become much more complex, requiring sophisticated techniques to compensate for the gravitational frequency shifts. The formation and structure of neutron stars would also be affected. These incredibly dense objects, formed when massive stars collapse, represent matter compressed to nuclear densities. The balance between gravitational collapse and the pressure from degenerate neutron matter determines the final size and mass of these exotic objects. In a slower light universe, this balance would shift, potentially allowing for neutron stars with different masses and radii than those possible in our current universe. Galaxy formation and evolution would feel the effects of altered gravity as well. Galaxies form when dark matter halos collapse under their own gravitational attraction, eventually gathering enough ordinary matter to begin forming stars. The rate and efficiency of this process depends on the strength of gravitational interactions and the speed at which gravitational instabilities can grow and spread. In a slower light universe, the cosmic web of dark matter that forms the large-scale structure of the universe might develop differently. Gravitational instabilities that grow from tiny quantum fluctuations in the early universe would evolve at different rates, potentially leading to a universe with different patterns of galaxy clustering and void formation. The phenomenon of gravitational lensing, where massive objects bend the path of light rays passing nearby, would also be affected. The amount of bending depends on both the mass of the lensing object and the speed of light. In a slower light universe, massive galaxies and galaxy clusters might produce stronger lensing effects, making distant objects appear more distorted or magnified when viewed through these cosmic telescopes. This enhanced lensing could actually be beneficial for astronomical observations, allowing us to see more distant and fainter objects than would be possible with weaker lensing effects. However, it would also make it more challenging to interpret lensing observations and extract information about the mass distribution of lensing objects. Tidal forces, which arise from differences in gravitational field strength across an extended object, would also behave differently. The tides on Earth, caused by the differential gravitational pull of the Moon and Sun on different parts of our planet, might be stronger or weaker depending on how the reduced speed of light affects the overall strength of gravitational interactions. More dramatically, the tidal forces near black holes and neutron stars, which can stretch objects into long, thin shapes in a process called spaghettification, would be modified. The tidal radius, the distance from a massive object where tidal forces become strong enough to disrupt smaller objects, would change, affecting everything from the formation of accretion disks to the survival of planets orbiting close to compact objects. The speed at which gravitational collapse occurs would also be affected. When a massive star runs out of nuclear fuel and begins to collapse under its own gravity, the process happens incredibly quickly, sometimes taking only seconds to compress an object the size of Earth down to a sphere just a few kilometers across. In a slower light universe, the dynamics of this collapse might be different, potentially affecting the types of compact objects that form and the amount of energy released in the process. Even the expansion of the universe itself would be affected by changes in the speed of light. The rate of cosmic expansion depends on the balance between the gravitational attraction of matter trying to slow the expansion and the mysterious dark energy that appears to be accelerating it. Changes to the speed of light could alter this delicate balance, potentially changing the fate of the universe over cosmic timescales. The cosmic microwave background radiation, the afterglow of the Big Bang that we observe today, carries information about the gravitational conditions in the early universe. In a slower light universe, the patterns of temperature fluctuations in this radiation would be different, reflecting the altered relationship between gravity, light, and the expansion of space in the first few 100,000 years after the Big Bang. As we contemplate these far-reaching changes, we see that gravity and light are not separate phenomena, but different aspects of the same underlying geometry of space-time. What happens when the force that binds galaxies together is altered? A shift in light speed might ripple through the very fabric of gravity, changing not just how objects fall toward each other, but how space and time themselves respond to the presence of matter and energy. The universe would become a fundamentally different place, where the cosmic dance between matter, energy, space, and time follows new choreography written in the language of slower light. In our modern world, we take for granted the nearly instantaneous flow of information across vast distances. A video call connects us with someone on the opposite side of the planet in real time. News from distant places reaches us within moments of occurring. Our GPS devices know our location with precision measured in meters, guided by signals from satellites orbiting 20,000 kilometers above our heads. Yet all of this technological magic depends on one fundamental truth. Information cannot travel faster than the speed of light. This cosmic speed limit is not merely a constraint on our technology. It is a fundamental law of nature that governs how cause and effect propagate through the universe. Every signal, every communication, every piece of information that travels from one place to another must respect this ultimate boundary. When we consider what would happen if the speed of light were to slow down, we are really asking how the very flow of information through space and time would be transformed. The relationship between light and information is deeper than it might first appear. Information, in the most fundamental sense, is about distinguishing between different possible states of a system. To communicate information, we must be able to send signals that represent these different states from one location to another. These signals, whether they are electromagnetic waves, sound waves, or any other form of disturbance, cannot travel faster than light. This is because sending information faster than light would violate causality itself, potentially allowing effects to precede their causes. Consider the simple act of sending a text message to a friend in another city. Your phone converts your words into digital signals, which are transmitted as electromagnetic waves to cell towers, then through fiber optic cables or satellite links to reach your friend's device. Every step of this process involves information traveling at the speed of light. The electrical signals in the circuits of your phone move at light speed. The radio waves carrying your message through the air propagate at light speed. Even the pulses of light traveling through fiber optic cables move at about 2/3 the speed of light in vacuum, slowed by their passage through glass. In a universe where light moved more slowly, this entire infrastructure of modern communication would be fundamentally transformed. A simple phone call across a continent might involve noticeable delays, turning real-time conversation into something more like an exchange of voice messages. Video conferences would become exercises in patience, as participants would need to wait for responses to their questions and comments. But the effects would extend far beyond mere inconvenience. The global positioning system that guides everything from smartphone maps to aircraft navigation depends on incredibly precise timing of signals from satellites. GPS works by measuring the time it takes for signals to travel from multiple satellites to a receiver on Earth. The receiver then uses these timing measurements to calculate its position through a process called trilateration. Currently, GPS signals travel from satellites to Earth in about 67 milliseconds. The system must account for relativistic effects that amount to microseconds per day, requiring atomic clocks accurate to nanoseconds. In a slower light universe, these signal travel times would be dramatically increased, and the relativistic effects would be much stronger. A GPS receiver might need to wait several seconds or even minutes to acquire enough satellite signals for a position fix. The increased signal delay would also make GPS less useful for applications requiring real-time positioning. Aircraft navigation, ship guidance, and autonomous vehicle systems would all need to account for the lag between their actual position and the position reported by GPS. The entire concept of real-time navigation would need to be reconsidered in a world where information about location takes significantly longer to propagate. Satellite communications would face even greater challenges. Current geostationary satellites orbit at an altitude of 35,786 kilometers above Earth's surface. Radio signals take about 240 milliseconds to make the round trip from Earth to a geostationary satellite and back. In a slower light universe, this delay could increase to several seconds or even minutes, making satellite internet and television broadcasting far less practical for interactive applications. The internet itself would be transformed by slower light. Currently, the speed of light creates subtle but measurable delays in global communications. A signal traveling from New York to London through undersea fiber optic cables takes about 65 milliseconds, while a signal routed through satellite links might take several hundred milliseconds. Financial trading firms pay enormous sums to reduce these delays by even a few milliseconds, because faster information flow can provide crucial advantages in rapidly changing markets. In a slower light universe, these delays would be measured in seconds or minutes rather than milliseconds. High-frequency trading, which currently relies on making thousands of transactions per second based on tiny market fluctuations, would become impossible. Stock markets would need to develop entirely new mechanisms for handling orders and executing trades when information about market conditions could be several minutes out of date. The social implications would be equally profound. Online gaming, video streaming, and social media platforms all depend on the rapid exchange of information between users and servers. A slower speed of light would introduce significant delays into these interactions, fundamentally changing how people communicate and interact online. Real-time collaboration tools would become less effective, potentially altering how businesses operate and how teams work together across different locations. Scientific research would also be affected in unexpected ways. Many modern physics experiments require precise synchronization of equipment located at different sites around the world. The detection of gravitational waves, for example, relies on comparing signals from multiple detectors located thousands of kilometers apart. The timing precision required for these measurements is so strict that even the current speed of light creates challenges that must be carefully accounted for. Radio astronomy, which studies the universe by observing radio waves from distant cosmic sources, would be fundamentally altered. Large radio telescope arrays, such as the Very Large Array in New Mexico, or the Event Horizon Telescope that captured the first image of a black hole, work by combining signals from multiple antennas located across vast distances. The timing precision required for this process depends on knowing exactly when signals arrive at each antenna, which requires accounting for the speed of light propagation delays. In a slower light universe, these propagation delays would be much larger, potentially making it more difficult to achieve the precise timing needed for high-resolution astronomical observations. On the other hand, the increased delays might make certain types of measurements easier, as the timing differences between different antennas would be larger and potentially easier to measure with existing equipment. The exploration of space would face new challenges and opportunities. Currently, communication with spacecraft exploring the outer solar system involves delays of hours or even days. The Voyager spacecraft, now beyond the edge of our solar system, is over 22 light hours away from Earth. Commands sent to Voyager take more than 22 hours to arrive, and any response takes another 22 hours to return. In a slower light universe, these communication delays would be even longer, making real-time control of distant spacecraft impossible. Space missions would need to rely even more heavily on autonomous systems and pre-programmed instructions. However, the reduced speed of light might also make certain types of space exploration easier, as the energy requirements for achieving high speeds relative to the new, slower speed of light might be more manageable. The timing systems that coordinate our modern world would require complete redesign. Everything from power grid synchronization to stock market operations relies on precise timekeeping across large distances. Currently, this is achieved through a combination of atomic clocks, GPS timing signals, and fiber optic networks that distribute time information at light speed. In a slower light universe, maintaining synchronized time across continents would become much more challenging. Even within individual cities, the slower propagation of information would create new challenges. Traffic control systems that coordinate signals across a metropolitan area would need to account for longer communication delays. Emergency response systems would be affected, as the time to communicate between dispatch centers and first responders would increase. The entire concept of real-time coordination would need to be redefined. Quantum communication systems, which promise ultra-secure information transfer using the strange properties of quantum mechanics, would also be affected. These systems rely on the transmission of quantum states encoded in photons, and their performance depends on the speed at which these quantum signals can travel. In a slower light universe, quantum communication networks would operate more slowly, potentially affecting their practical applications for secure communications. The development of artificial intelligence and machine learning systems might also be influenced by slower information propagation. Many modern AI systems rely on distributed computing, where calculations are performed across multiple processors or even multiple data centers located in different geographic regions. The increased communication delays in a slower light universe could make these distributed systems less efficient, potentially requiring new approaches to parallel computing and data processing. Research in fundamental physics would need to account for the new speed of information propagation. Particle accelerators, which currently smash particles together at nearly the speed of light, would face different constraints and opportunities. The detectors that observe these high-energy collisions rely on precise timing measurements to reconstruct what happened during each collision. Slower light would change the timing signatures of these events, requiring new analysis techniques and possibly revealing different aspects of particle physics. The concept of simultaneity would become even more observer-dependent than it already is. In our current universe, the relativity of simultaneity is only noticeable for observers moving at very high speeds relative to each other. In a slower light universe, these effects would become apparent at everyday speeds, making the coordination of events across different reference frames much more complex. Perhaps most profoundly, the slower speed of information propagation would affect our very understanding of causality and the nature of reality. Our intuitive notion that causes precede effects depends on information being able to travel from the location of a cause to the location of its effect. In a slower light universe, this causal connection would be stretched across longer time intervals, making the relationship between causes and effects more obvious and perhaps more philosophically significant. The speed of light is the speed at which information travels through our universe, and if it were to slow down, communication across the cosmos would be dramatically affected. What would that mean for our connection to the universe and to each other? It would mean that the very foundation of how we share knowledge, coordinate our actions, and maintain our technological civilization would need to be rebuilt from the ground up, creating a world where patience becomes not just a virtue, but a necessity for survival in an information-sparse cosmos. When we gaze up at the night sky, we are looking not just across space, but back through time itself. The light from distant stars and galaxies has traveled for millions, billions, or even tens of billions of years to reach our eyes. This cosmic time machine allows us to study the history of the universe, from its earliest moments to the present day. But what would happen to this grand cosmic story if the speed of light had been different throughout the universe's history? The relationship between light speed and cosmic time is fundamental to our understanding of the universe's age, size, and evolution. Currently, we estimate that the universe is approximately 13.8 billion years old, based on observations of the cosmic microwave background radiation and the distances to the most remote galaxies. This age measurement depends critically on knowing the speed of light and how it relates to the expansion of space itself. If the speed of light had been slower throughout cosmic history, our entire understanding of the universe's timeline would need to be reconsidered. The most distant galaxies we observe appear to us as they were when the universe was very young, perhaps only a few 100 million years after the Big Bang. The light from these ancient galaxies has been traveling toward us for over 13 billion years. In a universe where light had always moved more slowly, this same light would still be on its way to us, and the most distant objects we could observe would be much closer in both space and time. This would fundamentally alter our picture of cosmic evolution. The process of galaxy formation, starbirth, and the enrichment of the universe with heavy elements would appear to us to be happening on different timescales. Events that we currently believe took billions of years to unfold might appear to have happened much more quickly, simply because we would be seeing them from a time when the universe was much younger. The cosmic microwave background radiation, often called the afterglow of the Big Bang, carries crucial information about the conditions in the early universe. This radiation was emitted when the universe was only about 380,000 years old, at the moment when it first became transparent to light. The photons that make up this radiation have been traveling toward us ever since, carrying a fossilized record of what the universe was like at that crucial moment. In a slower light universe, the cosmic microwave background would still exist, but its properties would be different in several important ways. First, if light had always traveled more slowly, the radiation we observe today would have been emitted from a universe that was smaller and denser than we currently believe. The patterns of temperature fluctuations in this radiation, which tell us about the distribution of matter and energy in the early universe, would reflect these different conditions. More intriguingly, if the speed of light had changed over cosmic time, the cosmic microwave background might carry evidence of this change. The wavelength and intensity of this ancient light would be affected by any variation in light speed during its long journey to us. Cosmologists are already searching for such evidence in the detailed measurements of the cosmic microwave background, looking for clues about whether fundamental constants like the speed of light might have evolved over the lifetime of the universe. The expansion of the universe itself is intimately connected to the speed of light through Einstein's equations of general relativity. The rate at which space expands depends on the density of matter and energy within it, and this relationship is governed by equations that include the speed of light as a fundamental parameter. A different speed of light would imply a different relationship between the expansion rate and the energy content of the universe. Currently, we observe that the expansion of the universe is accelerating, driven by a mysterious component called dark energy that makes up about 68% of the universe's energy budget. This acceleration was discovered by observing distant supernovae, stellar explosions that serve as cosmic lighthouses because of their known intrinsic brightness. By comparing how bright these supernovae appear to us with how bright they should be based on their distance, astronomers can determine how the expansion rate has changed over cosmic time. In a universe with a different speed of light, these supernova observations would yield different conclusions about the expansion history. The relationship between distance and brightness depends on the speed of light, so a slower light speed would affect how we interpret these crucial measurements. Dark energy itself might appear to have different properties, or we might conclude that it doesn't exist at all, with the observed acceleration being instead a consequence of the altered light speed. The process of cosmic inflation, a period of extremely rapid expansion that occurred in the first tiny fraction of a second after the Big Bang, would also be affected by changes in the speed of light. Inflation theory explains many features of the universe we observe today, including its remarkable uniformity on large scales and the particular pattern of density fluctuations that eventually grew into galaxies and stars. The physics of inflation involves quantum fields evolving in curved spacetime, and the speed of light appears in the equations that govern this process. A different light speed during the inflationary epoch could lead to a universe with different properties. The scale of the density fluctuations, the duration of the inflationary period, and even whether inflation could occur at all might depend on the speed of light during those earliest moments. The formation of the first stars and galaxies would proceed differently in a universe with altered light speed. Stars form when clouds of gas collapse under their own gravity, eventually becoming dense and hot enough to ignite nuclear fusion. The balance between gravitational collapse and the pressure from hot gas depends on how quickly energy can be radiated away, and this process is fundamentally limited by the speed of light. In a slower light universe, energy would escape from collapsing gas clouds more slowly, potentially making star formation more efficient or changing the typical masses of the first stars. These primordial stars played a crucial role in cosmic evolution, producing the first heavy elements and eventually exploding as supernovae to seed the universe with the materials needed to form planets and life. The cosmic web, the large-scale structure of the universe consisting of galaxies connected by filaments of dark matter with vast empty voids between them, would develop differently if light speed were altered. This structure grows from tiny quantum fluctuations in the early universe through the gravitational attraction of dark matter. The rate at which these fluctuations grow depends on how quickly gravitational information can propagate, which is limited by the speed of light. Slower light would mean that gravitational instabilities would grow more slowly, potentially leading to a universe with different patterns of galaxy clustering. The sizes of galaxy clusters, the shapes of cosmic voids, and the overall architecture of the cosmic web might all be different. This could affect the formation of galaxies themselves, as galaxies form within the dark matter halos that make up the nodes of the cosmic web. The behavior of black holes on cosmic scales would also be transformed. Supermassive black holes, found at the centers of most galaxies, grow by accreting matter from their surroundings and by merging with other black holes. The rate of this growth depends on how quickly matter can fall into the black hole and how efficiently energy can be radiated away during the accretion process. In a slower light universe, the event horizons of black holes would be smaller, and the dynamics of matter falling into them would be different. This could affect the growth rate of supermassive black holes and their influence on galaxy formation. Many galaxies show evidence that their central black holes have significantly affected their evolution, regulating star formation and driving powerful outflows of gas. These processes might unfold differently if the fundamental speed limit of the universe were reduced. The cosmic distance ladder, the series of measurement techniques that astronomers use to determine distances to faraway objects, would require complete recalibration in a slower light universe. This ladder starts with direct geometric measurements to nearby stars and extends through various intermediate steps to the most distant galaxies. Each step depends on understanding how light travels and how brightness relates to distance. Standard candles, objects with known intrinsic brightness that serve as cosmic lighthouses, would appear different in a slower light universe. Type Ia supernovae, which currently provide our best measurements of cosmic acceleration, might have different light curves and peak brightnesses. Cepheid variable stars, which pulsate with periods related to their intrinsic brightness, might follow different period luminosity relationships. Even more fundamentally, the concept of look-back time, the idea that looking at distant objects means seeing them as they were in the past, would be altered. Currently, when we observe a galaxy 1 billion light-years away, we see it as it was 1 billion years ago. In a slower light universe, the same galaxy might appear to us as it was at a different epoch in cosmic history, fundamentally changing our understanding of how galaxies evolve over time. The cosmic neutrino background, a sea of low-energy neutrinos left over from the Big Bang, would also be affected by changes in the speed of light. While neutrinos travel at nearly the speed of light, their precise behavior depends on the fundamental constants of particle physics, including the speed of light. A different light speed might affect when neutrinos decoupled from the rest of matter in the early universe and what their current properties would be. Dark matter, the mysterious substance that makes up about 27% of the universe's matter and energy, might behave differently in a slower light universe. While dark matter particles are thought to interact only weakly with ordinary matter and light, their gravitational effects depend on how quickly gravitational fields can propagate. The formation of dark matter halos, the invisible scaffolding upon which galaxies form, might proceed at different rates or result in different structures. The ultimate fate of the universe, whether it will expand forever, eventually contract in a big crunch, or end in some other way, depends on the balance between the expansion rate and the gravitational attraction of matter within it. This balance is described by equations that fundamentally depend on the speed of light. A different light speed could tip this cosmic balance in unexpected directions, leading to a universe with a very different long-term destiny. Perhaps most intriguingly, if the speed of light were variable rather than constant, the universe itself might serve as a laboratory for detecting these changes. The light from distant quasars and gamma-ray bursts has traveled for billions of years to reach us. If the speed of light changed during this time, high-energy photons and low-energy photons from the same source might arrive at Earth at slightly different times, having been affected differently by the changing light speed during their journey. As we contemplate these cosmic implications, we see that the speed of light is not just a local phenomenon affecting our daily lives and technology. It is woven into the very fabric of cosmic evolution, determining how the universe expands, how structures form, and how information about the cosmos reaches us across the vast gulfs of space and time. The universe is expanding, and so is our understanding of its history. But slowing light would change not just the present, but the entire story of the cosmos, rewriting the grand narrative of cosmic evolution in ways we are only beginning to imagine. Deep beneath the surface of our everyday reality lies a strange and wonderful realm where the familiar rules of physics give way to something far more mysterious. This is the quantum world, where particles can exist in multiple states simultaneously, where the very act of observation changes reality, and where effects can seem to occur instantaneously across vast distances. Yet even in this bizarre quantum realm, the speed of light plays a fundamental role, governing the interactions between particles and setting the stage for the strangest phenomena in nature. To understand how a slower speed of light would affect the quantum world, we must first appreciate how intimately light and matter are connected at the smallest scales. Every interaction between charged particles, from the electrons in atoms to the quarks inside protons, is mediated by photons, the particles of light. These photons carry the electromagnetic force at exactly the speed of light, making this cosmic constant essential to the very structure of matter itself. Consider the humble hydrogen atom, the simplest and most abundant atom in the universe. It consists of a single proton surrounded by a single electron, held together by the electromagnetic force. The electron does not orbit the proton like a planet around the sun, as early atomic models suggested. Instead, it exists in a quantum state, described by a wave function that gives the probability of finding the electron at any particular location around the nucleus. The energy levels of this electron, the specific amounts of energy it can have, are determined by a delicate balance of quantum mechanical effects and electromagnetic interactions. The speed of light appears in the equations that govern these energy levels through a fundamental constant called the fine structure constant. This dimensionless number, approximately equal to 1 divided by 137, determines the strength of electromagnetic interactions and depends on the speed of light, the electric charge, and Planck's constant. In a slower light universe, the fine structure constant would have a different value, fundamentally altering the energy levels of electrons in atoms. This would change the wavelengths of light that atoms absorb and emit, potentially shifting the colors of stars and affecting the efficiency of processes like photosynthesis that depend on the absorption of specific wavelengths of light. The quantum mechanical uncertainty principle, one of the most fundamental features of quantum physics, relates the uncertainty in a particle's position to the uncertainty in its momentum. This principle emerges from the wave-like nature of matter and is intimately connected to the speed of light through the structure of space-time itself. In a slower light universe, the relationship between space and time would be different, potentially affecting how quantum uncertainty manifests at different scales. Quantum field theory, our most complete description of how particles interact, treats all particles as excitations in underlying quantum fields that permeate all of space. Photons are excitations in the electromagnetic field, electrons are excitations in the electron field, and so on. The speed of light appears throughout the equations of quantum field theory, determining how these fields propagate through space and how they interact with each other. In a slower light universe, the propagation of quantum fields would be fundamentally altered. Virtual particles, the temporary quantum fluctuations that mediate forces between real particles, would behave differently. These virtual particles exist for incredibly brief moments, limited by the uncertainty principle and the speed at which information can propagate. Slower light would extend the lifetime and range of some virtual particle interactions while constraining others. The phenomenon of quantum entanglement, perhaps the strangest aspect of quantum mechanics, would also be affected by changes in the speed of light. When two particles become entangled, measuring the quantum state of one particle instantly determines the state of the other, regardless of the distance between them. This seems to violate the speed of light limit, but it does not actually allow usable information to be transmitted faster than light. In a slower light universe, the apparent instantaneous nature of quantum entanglement would become even more striking. The correlations between entangled particles would still occur immediately, but the speed limit for transmitting classical information about these correlations would be reduced. This could make quantum entanglement more useful for certain applications, while making others more challenging. Quantum tunneling, the ability of particles to pass through barriers that should be impossible to cross according to classical physics, depends on the wave-like properties of matter and the uncertainty principle. The probability of tunneling depends on the height and width of the barrier and the mass and energy of the particle. In a slower light universe, the relationship between energy and momentum would be different, potentially affecting tunneling probabilities and the rates of quantum processes that depend on tunneling. nuclear physics would feel the effects of slower light in several ways. The strong nuclear force that holds protons and neutrons together in atomic nuclei is mediated by particles called gluons, which travel at the speed of light. The dynamics of nuclear reactions, radioactive decay, and the formation of heavy elements in stars all depend on the precise balance between the strong force, electromagnetic force, and the weak nuclear force. Changes to the speed of light could alter this balance, potentially affecting the stability of atomic nuclei and the rates of nuclear processes. Elements that are stable in our current universe might become unstable, while others that quickly decay might become more long-lived. This could have profound implications for the formation of heavy elements in stars and the possibility of complex chemistry and life. The weak nuclear force, responsible for certain types of radioactive decay and essential to the fusion processes that power stars, is also mediated by particles that travel at light speed. In a slower light universe, weak force interactions might proceed at different rates, affecting everything from the fusion reactions in stellar cores to the decay of unstable particles created in cosmic ray interactions. Quantum chromodynamics, the theory that describes the strong force and the behavior of quarks and gluons inside protons and neutrons, would be fundamentally altered by changes in the speed of light. The confinement of quarks inside hadrons, the asymptotic freedom that allows quarks to move freely at very short distances, and the entire spectrum of particle physics would need to be reconsidered. The creation and annihilation of particle-antiparticle pairs, a fundamental feature of quantum field theory, depends on the relationship between energy and mass expressed in Einstein's equation E equals mc squared. In a slower light universe, the energy available for pair creation would be reduced, potentially affecting the rates of high-energy processes and the behavior of matter in extreme environments like the cores of neutron stars or the vicinity of black holes. Quantum electrodynamics, the quantum theory of electromagnetic interactions, makes predictions about the behavior of electrons and photons that have been tested to extraordinary precision. The anomalous magnetic moment of the electron, for example, has been measured and calculated to agree to better than 1 part in a trillion. These precise predictions depend on the exact value of the fine structure constant and would be different in a slower light universe. The Casimir effect, a quantum phenomenon where two parallel metal plates in vacuum experience an attractive force due to quantum fluctuations of the electromagnetic field, would be modified by changes in the speed of light. The strength of this force depends on the density of quantum modes in the electromagnetic field, which in turn depends on the speed of light. This could affect the design of sensitive quantum devices and microelectromechanical systems. Quantum computing, which harnesses the strange properties of quantum mechanics to perform certain calculations exponentially faster than classical computers, would face new challenges and opportunities in a slower light universe. Quantum algorithms depend on the precise control and manipulation of quantum states, often involving the interaction of matter with carefully timed laser pulses. Changes to the speed of light could affect the timing and efficiency of these operations. The decoherence time, the period during which a quantum system can maintain its delicate quantum properties before being disrupted by interactions with its environment, might be affected by slower light. Photons from the environment constantly interact with quantum systems, gradually destroying their quantum coherence. If these photons moved more slowly, the rate of decoherence might change, potentially making quantum computers easier or harder to build and operate. Quantum communication protocols, which use quantum properties like entanglement to enable ultra-secure information transfer, would need to be redesigned for a slower light universe. The no-cloning theorem, which prevents quantum information from being perfectly copied, and the principles that enable quantum key distribution would still hold, but the practical implementation of these protocols would be affected by the reduced speed of information propagation. The quantum vacuum, far from being empty space, is filled with virtual particle pairs constantly appearing and disappearing due to quantum fluctuations. These vacuum fluctuations contribute to measurable effects like the Lamb shift in atomic energy levels and the anomalous magnetic moments of particles. In a slower light universe, the energy density and structure of these vacuum fluctuations would be different, potentially affecting the masses and properties of fundamental particles. Quantum gravity, the long-sought theory that would unify quantum mechanics with general relativity, remains one of the greatest unsolved problems in physics. Various approaches to quantum gravity, from string theory to loop quantum gravity, make different predictions about how space-time behaves at the smallest scales. In a slower light universe, these theories might make different predictions, potentially providing new ways to test and distinguish between competing approaches. The hierarchy problem, the question of why gravity is so much weaker than the other fundamental forces, might have different solutions in a universe with altered light speed. Extra dimensions, supersymmetry, and other exotic possibilities proposed to explain this hierarchy could manifest differently or become unnecessary if the fundamental relationships between forces were changed. Particle accelerators, our primary tools for probing the quantum world at high energies, would face new constraints and opportunities in a slower light universe. The maximum energy that could be achieved would be lower in absolute terms, but particles could reach higher fractions of the reduced light speed with the same energy input. This might make some experiments easier while making others impossible. The standard model of particle physics, our current best theory of fundamental particles and forces, includes 19 free parameters that must be determined experimentally. Many of these parameters depend on the speed of light, either directly or indirectly. In a slower light universe, these parameters would have different values, potentially leading to a very different spectrum of particles and forces. As we explore these quantum implications, we see that the speed of light is not just a limit on how fast things can move. It is woven into the very fabric of quantum reality, determining how particles interact, how atoms form, and how the fundamental forces of nature operate. At the quantum scale, light behaves in mysterious ways, but if its speed were altered, could it lead to new, unimagined phenomena? The answer lies in understanding that the quantum world is not separate from our everyday reality, but is the foundation upon which everything else is built, and changing that foundation would transform the entire structure of existence itself. Our modern world is built upon a foundation of technologies that depend fundamentally on the speed of light. From the smartphone in your pocket to the satellites orbiting overhead, from the fiber optic cables carrying internet traffic across oceans to the GPS navigation system guiding your car, virtually every aspect of our technological civilization relies on electromagnetic signals traveling at light speed. If that cosmic constant were to slow down, the ripple effects would transform not just individual devices, but the entire technological landscape that shapes our daily lives. Consider the simple act of making a phone call. When you speak into your phone, your voice is converted into electrical signals that travel through circuits at nearly the speed of light. These signals are then transmitted as radio waves through the air, bouncing between cell towers and switching centers before reaching their destination. The entire process, from your voice entering the microphone to the sound emerging from the recipient's speaker, takes place in what seems like an instant because electromagnetic signals move so incredibly fast. In a slower light universe, this seamless communication would become noticeably delayed. A phone conversation across a city might involve a lag of several seconds between speaking and being heard. International calls could involve delays of minutes, transforming real-time conversation into something more like an exchange of audio messages. The psychological and social impact of this change would be profound, fundamentally altering how people communicate and connect with each other across distances. The internet, often called the nervous system of our modern civilization, would be dramatically affected by slower light. Currently, data travels through fiber optic cables at about 2/3 the speed of light in vacuum, slowed by its passage through glass. Even at this reduced speed, information can travel from New York to London in about 65 milliseconds, fast enough to enable real-time video calls, online gaming, and financial trading. In a slower light universe, these fiber optic networks would carry information much more slowly. A web page request might take several seconds or even minutes to reach its destination and return with the requested data. Streaming video would become practically impossible over long distances, as the delay between requesting data and receiving it would be too long to maintain smooth playback. The entire concept of cloud computing, where data and applications are accessed from remote servers, would need to be reconsidered. Social media platforms, which currently enable near instantaneous global communication and real-time sharing of information, would be forced to adapt to a world where information moves more slowly. The viral spread of news and ideas across the internet would proceed at a more measured pace, potentially affecting everything from political movements to marketing campaigns to the way scientific discoveries are shared and verified. Online gaming, particularly multiplayer games that require real-time coordination between players in different locations, would face fundamental challenges. The competitive gaming industry, which relies on split-second timing and reaction speeds, might need to develop entirely new genres and gameplay mechanics adapted to the slower pace of information exchange. The concept of lag, already a concern for gamers, would become a dominant factor in game design. The global positioning system that guides everything from smartphones to aircraft navigation represents one of the most sophisticated technological achievements of our time. GPS works by precisely timing signals from multiple satellites as they travel to receivers on Earth. The system currently achieves accuracy measured in meters by accounting for relativistic effects that amount to mere microseconds per day. In a slower light universe, GPS signals would take much longer to travel from satellites to Earth, and the relativistic effects would be dramatically stronger. A GPS receiver might need to wait several minutes to acquire enough satellite signals for a position fix, making real-time navigation impossible. Aircraft, ships, and autonomous vehicles would all need alternative navigation methods, potentially returning to older technologies like radio beacons and inertial navigation systems. The financial industry, which increasingly relies on high-frequency trading and split-second decision-making, would be fundamentally transformed. Currently, trading firms pay enormous sums to reduce communication delays by even milliseconds, because faster access to market information can provide crucial advantages. In a slower light universe, these delays would be measured in seconds or minutes rather than milliseconds, making high-frequency trading impossible and forcing the development of entirely new trading strategies and market mechanisms. Satellite communications, which connect remote regions of the world and enable global broadcasting, would face severe challenges. Current geostationary satellites orbit at an altitude where radio signals take about 240 milliseconds to make the round trip from Earth to satellite and back. In a slower light universe, this delay could increase to several seconds or even minutes, making interactive satellite communications impractical for many applications. Television broadcasting via satellite would need to abandon live programming in favor of pre-recorded content, as the delays would make real-time interaction between studios and remote locations impossible. Satellite internet, already challenged by latency issues, would become unsuitable for interactive applications, potentially stranding remote communities that rely on satellite connectivity. Computer processors, the brains of our digital devices, are fundamentally limited by the speed at which electrical signals can travel between different components. Modern processors operate at clock speeds measured in billions of cycles per second, with each cycle limited by how quickly signals can propagate through the microscopic circuits etched into silicon chips. In a slower light universe, these propagation delays would become the dominant factor limiting processor performance. Computer architects would need to develop new designs that minimize the distances signals must travel, potentially leading to radically different processor architectures. The trend towards smaller and faster processors might reverse, as the benefits of miniaturization would be offset by the reduced speed of signal propagation. Supercomputers, which achieve their enormous computational power by coordinating the work of thousands or millions of individual processors, would face particularly severe challenges. These machines rely on high-speed interconnects to share data between processors, often using optical fiber links operating at light speed. In a slower light universe, the time required to coordinate work between different parts of a supercomputer could exceed the time needed to perform the actual calculations. The development of quantum computers, which promise to solve certain types of problems exponentially faster than classical computers, would also be affected. Quantum computers rely on the precise manipulation of quantum states using carefully timed laser pulses and electromagnetic fields. The reduced speed of light could affect the timing and efficiency of these operations, potentially making some quantum algorithms more difficult to implement while opening up new possibilities for others. Fiber optic communications, the backbone of our global information infrastructure, would require complete redesign. Current fiber optic systems use sophisticated techniques to maximize the amount of information that can be transmitted through a single optical fiber, including wavelength division, multiplexing, and advanced modulation schemes. In a slower light universe, these systems would need to be optimized for the new propagation speed, potentially requiring different wavelengths, pulse shapes, and signal processing techniques. The telecommunications industry would need to develop new protocols and technologies adapted to the slower information propagation. Error correction codes, which currently account for occasional transmission errors, would need to be redesigned for longer transmission delays. Network routing algorithms would need to consider not just the shortest path between 2 points, but also the time delays involved in different routing options. Radar and LiDAR systems, which use electromagnetic waves to detect and measure distances to objects, would be fundamentally altered by slower light. These systems work by timing how long it takes for signals to travel to a target and return. Current radar systems can track fast-moving objects like aircraft and missiles with remarkable precision. In a slower light universe, the longer signal travel times would reduce the temporal resolution of these systems, potentially affecting their ability to track rapidly changing targets. Medical imaging technologies that rely on electromagnetic radiation, such as X-ray machines, MRI scanners, and ultrasound devices, would face new challenges and opportunities. While X-rays and other forms of electromagnetic radiation would still interact with matter in similar ways, the reduced speed of light could affect the timing and synchronization of imaging sequences, particularly for techniques that require precise coordination between signal transmission and detection. Radio astronomy, which studies the universe by observing radio waves from distant cosmic sources, would need to adapt to the slower propagation speed. Very long baseline interferometry, a technique that combines signals from radio telescopes separated by thousands of kilometers, relies on precise timing to achieve high-resolution images of distant objects. The increased signal propagation delays in a slower light universe might actually make certain types of measurements easier, as the timing differences between different telescopes would be larger and potentially easier to measure. The development of new energy technologies would also be affected. Solar panels, which convert sunlight into electricity, rely on the photovoltaic effect, where photons knock electrons loose from atoms in semiconductor materials. The energy of photons depends on their frequency and the speed of light, so slower light could affect the efficiency of solar energy conversion. potentially requiring new materials and designs optimized for the altered light speed. Laser technology, which has applications ranging from industrial cutting and welding to medical surgery and scientific research, would need to be reconsidered. The coherence properties of laser light, which make it useful for precision applications, depend on the relationship between wavelength and frequency that is governed by the speed of light. Different laser designs might be needed to achieve the same performance in a slower light universe. Optical computing, an emerging technology that uses light instead of electricity to process information, would face both challenges and opportunities. While the reduced speed of light would slow down optical signal propagation, it might also enable new types of optical devices and computing architectures that take advantage of the altered relationship between light and matter. The space industry would need to completely rethink its approach to communication and navigation. Currently, spacecraft use radio signals to communicate with Earth and to navigate through the solar system. The increased communication delays in a slower light universe would make real-time control of spacecraft impossible, requiring much more sophisticated autonomous systems and pre-programmed mission sequences. Interplanetary missions would face even greater challenges, as the already substantial communication delays to distant planets would be further increased. A mission to Mars, which currently involves communication delays of up to 24 minutes depending on the planet's positions, might face delays of hours or even days in a slower light universe. The development of advanced materials and nanotechnology would also be affected by slower light. Many modern materials derive their properties from the precise arrangement of atoms and molecules, which is determined by electromagnetic interactions that propagate at light speed. Slower light could affect the stability and properties of these materials, potentially requiring the development of entirely new classes of materials optimized for the altered electromagnetic environment. Perhaps most intriguingly, the challenges posed by slower light might drive the development of revolutionary new technologies that we cannot currently imagine. Just as the limitations of early computers led to the development of integrated circuits and microprocessors, the constraints of a slower light universe might inspire innovations that work around or even take advantage of the reduced speed of information propagation. Our world depends on the speed of light for everything from navigation to communication. And if that foundation shifted, would our technological advances adapt, or would they unravel? The answer would depend on our ability to reimagine and rebuild our technological civilization from the ground up, creating new tools and systems designed for a universe where information moves more slowly, but human ingenuity and creativity remain as boundless as ever. As we journey deeper into the implications of a slower speed of light, we find ourselves confronting questions that extend far beyond the realm of physics and technology. We enter a space where science meets philosophy, where the fundamental nature of reality itself comes into question. What does it truly mean for the speed of light to change? What would such a transformation tell us about the deepest principles that govern our universe and our place within it? The speed of light is more than just a physical constant. It is a fundamental feature of the architecture of reality itself. In our current understanding, this cosmic speed limit defines the very structure of space and time, determining how cause and effect flow through the universe and setting the boundaries of what is possible. To contemplate its alteration is to question the most basic assumptions we make about the nature of existence. Consider what the constancy of light speed has meant for our understanding of truth and reality. For over a century, the invariant speed of light has served as an anchor point for physics, a universal constant that remains the same for all observers regardless of their motion. This constancy has given us confidence that there are indeed universal truths, fundamental principles that apply everywhere and everywhen in the cosmos. If the speed of light were to slow down, this philosophical foundation would be shaken. We would be forced to confront the possibility that what we consider to be the most fundamental constants of nature might not be constant at all. This realization would challenge our entire approach to understanding the universe, forcing us to question whether any aspect of reality is truly permanent and unchanging. The relationship between time and existence would take on new meaning in a slower light universe. Our current conception of time is intimately linked to the speed of light through the structure of space-time. Time is not simply the ticking of clocks or the progression of events, but a dimension of reality that is fundamentally intertwined with space through the cosmic speed limit. In a universe where light moves more slowly, our very experience of temporal flow might be altered in ways that challenge our most basic intuitions about the nature of time. We often think of time as flowing like a river, carrying us from past through present toward future. But Einstein's relativity showed us that this flow is not universal. Different observers can experience time passing at different rates, and what counts as simultaneous depends on your reference frame. In a slower light universe, these relativistic effects would be magnified, making the subjective nature of time more apparent in everyday experience. This could fundamentally alter how conscious beings perceive reality and their place within it. If time dilation became noticeable at ordinary speeds, our intuitive sense of shared temporal experience would be challenged. Different people, moving at different velocities, would literally experience time differently. The concept of a universal now would become not just a theoretical abstraction, but a practically meaningless notion. The implications for consciousness itself are profound. Our sense of self, our memories, and our planning for the future all depend on a coherent experience of temporal flow. In a slower light universe where time passes differently for different observers, the nature of personal identity might need to be reconsidered. Are you the same person if you experience time at a different rate than others? How would relationships and society function when different individuals age at measurably different rates depending on their motion? The question of free will, already one of the most challenging problems in philosophy, would take on new dimensions in a slower light universe. Our current understanding of causality is built around the principle that causes must precede their effects, with information about causes propagating no faster than light speed. In a universe where light moves more slowly, the causal connections between events would be stretched across longer time intervals, making the relationship between cause and effect more obvious, but also more constrained. This extended causality might actually strengthen arguments for determinism, as the delayed propagation of causal influences would create more obvious chains of cause and effect. Alternatively, it might provide more room for quantum indeterminacy to influence macroscopic events, as the longer time delays could allow quantum effects to accumulate and influence larger scale phenomena. The nature of knowledge and observation would be fundamentally altered. In our current universe, the finite speed of light already means that all our observations of distant objects show us the past rather than the present. In a slower light universe, this separation between observation and reality would be dramatically enhanced. Our knowledge of the universe would become even more obviously historical, with even nearby events taking longer to reach us. This enhanced delay between events and our knowledge of them would affect how we understand causation, prediction, and scientific methodology. The scientific method relies on the ability to observe phenomena, form hypotheses, and test predictions. In a slower light universe, the time delays involved in observation and communication would make collaborative science more challenging, potentially requiring new approaches to experimental verification and peer review. The philosophical implications extend to our understanding of unity and connection. Currently, the finite speed of light creates a cosmic horizon beyond which we cannot see or communicate. In a slower light universe, this horizon would be much closer, limiting our observable universe and reducing our sense of connection to the larger cosmos. We would be more isolated, both from distant regions of space and from events in our cosmic neighborhood. This isolation might foster a more local, immediate philosophy of existence. If the effects of distant events took much longer to reach us, and if our ability to influence distant regions were more limited, we might develop a more focused appreciation for our immediate environment and relationships. The cosmic perspective that has emerged from modern astronomy, with its emphasis on our connection to the larger universe, might give way to a more Earth-centered or even more locally centered worldview. The question of meaning and purpose in the universe would also be affected. Many people find meaning in feeling connected to something larger than themselves, whether that is their community, their planet, or the cosmos as a whole. In a slower light universe, these connections would be attenuated by the increased time delays and communication difficulties. The sense of being part of a vast, interconnected cosmic web might be replaced by a more immediate but more limited sense of local connection and purpose. The concept of simultaneity, already challenged by relativity, would become even more problematic in a slower light universe. The notion that events can happen at the same time depends on our ability to coordinate clocks and share information about when things occur. With slower light, this coordination would become much more difficult, making simultaneity even more obviously observer-dependent. This could affect our understanding of social and political organization. Democratic processes, for example, often depend on the ability to coordinate actions across large groups of people. If information propagation were much slower, the logistics of organizing societies and making collective decisions would become more challenging. We might see the emergence of more decentralized, locally autonomous forms of organization adapted to the slower pace of information exchange. The relationship between individual and collective identity might also shift. In our current highly connected world, individual identity is often shaped by participation in global cultures and communities. In a slower light universe, these global connections would be weakened, potentially leading to stronger local identities, but weaker cosmopolitan ones. The nature of truth and verification would take on new significance. In science and philosophy, we often rely on independent verification of observations and experiments. Multiple observers or researchers confirm findings to establish their validity. In a slower light universe, this process of verification would be slowed down by the increased communication delays, potentially changing how we establish and validate knowledge. The concept of universal laws of nature might need to be reconsidered. If fundamental constants like the speed of light can change, what does this say about the universality of physical laws? Are the principles we observe in our local region of space and time truly universal? Or might they vary in ways we have not yet discovered? This uncertainty could lead to a more humble, tentative approach to scientific knowledge, acknowledging that our current understanding might be more limited and local than we currently believe. The problem of consciousness and its relationship to the physical world would be complicated by slower light. Many theories of consciousness involve information processing and integration across different parts of the brain. If the speed of information propagation were reduced, this could affect how consciousness emerges from neural activity. The timing of neural signals, already crucial for brain function, would be altered in ways that might change the nature of conscious experience itself. The aesthetic and artistic implications should not be overlooked. Much of human art and culture is built around rhythm, timing, and the coordination of events across space and time. Music, dance, theatre, and film all depend on precise timing and synchronization. In a slower light universe, these art forms would need to adapt to new constraints and possibilities, potentially giving rise to entirely new forms of artistic expression, adapted to the altered pace of information flow. The question of human enhancement and the limits of biological adaptation would become more pressing. If technological solutions to communication and coordination became more difficult due to slower light, there might be increased interest in biological or cybernetic enhancements that could help humans adapt to the new constraints. This could accelerate debates about human nature, enhancement, and the boundaries between natural and artificial intelligence. Perhaps most fundamentally, a slower speed of light would force us to confront the contingency of our existence. The fact that physical constants could be different reminds us that the universe as we know it is not inevitable, but rather one possibility among many. This cosmic humility might lead to a greater appreciation for the particular configuration of natural laws that has made complexity, life, and consciousness possible. The philosophical implications ripple outward into questions about the meaning of progress, the nature of time, the possibility of objective truth, and the relationship between mind and matter. In contemplating a universe with slower light, we are really contemplating the deepest questions about reality itself. The speed of light is a universal constant that defines the flow of time. And if that constant were to change, how would we perceive the world around us and our place within it? We would find ourselves in a universe that challenges our most basic assumptions about the nature of existence, forcing us to develop new ways of understanding ourselves and our relationship to the cosmos that surrounds us. As we stand at the threshold of understanding what a slower speed of light might mean for our universe, we find ourselves gazing not just backward at the implications for known physics, but forward into the vast landscape of undiscovered possibilities. The prospect of a variable or altered speed of light opens doors to new theories, revolutionary discoveries, and fundamental insights that could transform our understanding of reality itself. In contemplating this transformed universe, we are really exploring the endless frontier of human knowledge and the profound mysteries that still await our discovery. The history of physics has been marked by moments when seemingly impossible ideas revolutionized our understanding of the world. Newton's insight that the same force governing falling apples also guides planetary orbits. Einstein's realization that space and time are not separate, but woven together into a single fabric. The quantum revolution that revealed the probabilistic nature of reality at its smallest scales. Each breakthrough initially seemed to contradict common sense, yet each opened up new realms of understanding and possibility. The discovery that the speed of light could vary would represent another such revolutionary moment. It would force physicists to reconsider not just individual theories and equations, but the entire framework within which we understand the universe. This process of reconceptualization would likely lead to insights and discoveries that we cannot currently imagine, just as the development of relativity and quantum mechanics revealed phenomena that earlier scientists could never have anticipated. One of the most immediate consequences would be a renaissance in theoretical physics. The mathematical frameworks that describe our current understanding of space, time, matter, and energy all assume that the speed of light is constant. Variable light speed would require the development of entirely new mathematical tools and conceptual approaches. Physicists would need to create new geometries, new ways of describing the relationship between space and time, and new equations that could accommodate the changing cosmic speed limit. This theoretical revolution would likely reveal connections between phenomena that currently seem unrelated. Just as Einstein's relativity showed that mass and energy are different aspects of the same thing, and that space and time are unified, a theory of variable light speed might reveal new unities in nature. Perhaps the fundamental forces that appear distinct in our current universe would be revealed as different manifestations of a single underlying principle. Perhaps the mysterious dark matter and dark energy that dominate our cosmos would find natural explanations in a framework where light speed can change. The field of cosmology would be completely transformed. Our current understanding of the universe's history, from the Big Bang through cosmic inflation to the present day, is built on the assumption that physical constants have remained fixed throughout cosmic time. If the speed of light could vary, cosmologists would need to reconstruct the entire story of cosmic evolution, considering how changing light speed might have affected the formation of the first atoms, the ignition of the first stars, and the assembly of the first galaxies. This reconstruction might resolve some of the deepest puzzles in modern cosmology. The horizon problem, which questions how distant regions of the universe can have such similar temperatures despite being too far apart to have ever communicated, might find new solutions if light speed were different in the early universe. The flatness problem, concerning why the geometry of space appears to be so precisely balanced, might be explained by the evolution of fundamental constants over cosmic time. The mystery of dark energy, the unknown force that appears to be accelerating the expansion of the universe, might also find resolution in theories of variable light speed. Some cosmologists have already proposed that what we interpret as dark energy might actually be evidence of changing fundamental constants. If the speed of light has been increasing over cosmic time, this could create the appearance of accelerating expansion without requiring any new form of energy. Quantum mechanics would undergo equally profound development. The uncertainty principle, the wave-particle duality of matter and energy, and the strange phenomenon of quantum entanglement all depend on relationships that involve the speed of light. Variable light speed might reveal new aspects of quantum reality that are currently hidden from us. Perhaps the apparent randomness of quantum measurements would prove to be less random than we thought. Perhaps new forms of quantum entanglement would become possible, enabling technologies and capabilities that we cannot currently envision. The search for a theory of quantum gravity, the holy grail of modern physics that would unify the quantum world with Einstein's description of space-time, might find new avenues of exploration. Many approaches to quantum gravity, from string theory to loop quantum gravity to causal set theory, make predictions about how space-time behaves at the smallest scales. Variable light speed might provide new ways to test these theories and distinguish between competing approaches. String theory, which proposes that the fundamental constituents of reality are tiny vibrating strings rather than point particles, might find new validation or face new challenges in a variable light speed universe. The extra dimensions that string theory requires might become more accessible to observation if the speed of light could change in ways that affect how these dimensions are hidden from our everyday experience. The concept of emergent space-time, the idea that space and time themselves might arise from more fundamental underlying structures, would take on new significance. If the speed of light can change, it suggests that the space-time we observe might not be as fundamental as we thought. This could support theories in which space and time emerge from quantum information, quantum entanglement, or other more basic building blocks of reality. The study of black holes would be revolutionized by variable light speed. These cosmic laboratories, where matter and energy exist under the most extreme conditions in the universe, already challenge our understanding of physics. If the speed of light could vary near black holes, it might resolve paradoxes like the information paradox, which concerns what happens to information that falls into a black hole. Perhaps the apparent loss of information could be explained by changes in light speed that alter how information propagates near the event horizon. Wormholes, hypothetical shortcuts through space-time that could connect distant regions of the universe, might become more plausible in a variable light speed framework. Current theories suggest that traversable wormholes would require exotic matter with negative energy density to keep them stable. Variable light speed might provide alternative mechanisms for wormhole stability, potentially making these cosmic highways more physically realistic. The search for extraterrestrial intelligence would take on new dimensions in a universe where light speed could vary. Our current strategies for detecting alien civilizations assume that any technological species would use electromagnetic signals that propagate at light speed. If advanced civilizations had learned to manipulate the speed of light, they might use communication methods that we have not yet considered. This could explain why our searchers have not yet detected obvious signs of extraterrestrial technology. Conversely, variable light speed might provide new opportunities for interstellar communication and travel. If civilizations could create regions of space where light travels faster, this might enable practical interstellar voyages and real-time communication across galactic distances. The development of such technologies would represent one of the greatest achievements in the history of any species. The nature of time itself would become a subject of renewed investigation. Our current understanding treats time as a dimension similar to space, but variable light speed might reveal that time has properties and behaviors that we have not yet discovered. Perhaps time could be manipulated, stored, or transferred in ways that would seem impossible in our current framework. Perhaps the arrow of time, the apparent asymmetry between past and future, would prove to be more flexible than we imagine. Consciousness and its relationship to physical reality would become an even more intriguing frontier. Some theories suggest that consciousness emerges from information processing and integration across different parts of the brain. If the speed of light could be controlled or modified, this might enable new forms of information processing that could enhance or transform consciousness itself. The boundary between biological and artificial intelligence might blur as new physical principles enable unprecedented computational capabilities. The development of new technologies would accelerate in unexpected directions. Materials science might discover substances with properties that depend on local variations in light speed. Energy generation and storage might exploit the relationship between mass and energy in new ways. Transportation systems might harness variable light speed for propulsion or navigation. Computing might undergo a revolution comparable to the transition from mechanical calculators to electronic computers. If the speed of light could be controlled at microscopic scales, this might enable new forms of optical computing that operate far faster than current electronic systems. Quantum computers might achieve new levels of performance by manipulating the propagation of quantum information. The exploration of consciousness expanding substances and practices might find new scientific foundations. Many spiritual and philosophical traditions speak of altered states of consciousness in which time seems to flow differently or space appears to have different properties. If the speed of light could indeed vary, this might provide a physical basis for understanding these experiences and perhaps for developing new methods of consciousness exploration. The implications for artificial intelligence would be profound. Machine intelligence systems that could manipulate fundamental constants like light speed might achieve capabilities that transcend our current imagination. Such systems might be able to process information, solve problems, and interact with reality in ways that would seem godlike by current standards. The relationship between mathematics and physical reality would require fundamental reconsideration. Mathematics has been called the language of the universe, but variable light speed might reveal that this language is richer and more flexible than we realized. New mathematical structures might be needed to describe reality, potentially leading to insights that transform mathematics itself. The search for a theory of everything, a single framework that could explain all physical phenomena, might find new directions. Current attempts to unify the fundamental forces and explain the properties of matter and energy assume fixed physical constants. Variable light speed might be the key insight needed to achieve this ultimate goal of physics. Perhaps most excitingly, the discovery of variable light speed might reveal that our universe is far stranger and more wonderful than we currently imagine. Just as the development of telescopes revealed that our Earth is one planet among many orbiting one star, among billions in one galaxy, among countless others, the discovery that light speed can change might reveal new levels of cosmic reality. Perhaps our universe is one bubble in a vast multiverse where different regions have different physical laws. Perhaps consciousness and intelligence play fundamental roles in shaping physical reality. The tools and methods of experimental physics would need to evolve to test these new theories. particle accelerators might be designed to create conditions where light speed variations could be observed. Space-based experiments might search for evidence of light speed changes across cosmic distances and timescales. New detection methods might be developed to observe phenomena that are currently beyond our technological reach. The future of physics holds endless possibilities, and discovering that the speed of light is not fixed could be one of the most profound revelations yet. It would open doorways to understanding aspects of reality that we cannot currently imagine, challenging our deepest assumptions about the nature of existence and revealing new frontiers for human exploration and discovery. In such a universe, the journey of scientific discovery would be far from over. Instead, it would be just beginning, with infinite mysteries waiting to be explored and infinite possibilities waiting to be discovered by curious minds willing to question everything and imagine the impossible. As our journey through the implications of slower light draws to a gentle close, we find ourselves not at an ending, but at a threshold. We have traveled together through landscapes of possibility, exploring how a simple change to one cosmic constant could transform everything, from the quantum realm to the vast expanses of space, from the nature of time itself to the deepest philosophical questions about existence and consciousness. The speed of light, we have discovered, is far more than just a number in a physics textbook. It is the heartbeat of the cosmos, the rhythm that coordinates the dance between space and time, matter and energy, cause and effect. It determines how quickly information can flow across the universe, how strongly gravity can bend the fabric of space-time, and how the fundamental forces of nature interact to create the rich tapestry of reality that surrounds us. In contemplating what would happen if this cosmic constant were to slow down, we have glimpsed the profound interconnectedness of all things. We have seen how altering one seemingly simple parameter would send ripples through every aspect of existence, from the behavior of subatomic particles to the evolution of galaxies, from the functioning of our technology to the nature of our consciousness. Yet perhaps the most important discovery of our exploration is not any specific prediction about how a slower light universe would behave, but rather the recognition of how much mystery still surrounds us. Every answer we have uncovered has revealed new questions. Every explanation has pointed toward deeper layers of unknown territory waiting to be explored. This is the true spirit of scientific discovery. It is not about reaching final answers or ultimate explanations, but about embracing the endless process of learning, questioning, and wondering. Each generation of scientists and thinkers builds upon the insights of those who came before, adding new pieces to the ever-expanding puzzle of understanding, while simultaneously discovering that the puzzle is far larger and more intricate than anyone had previously imagined. The universe we inhabit is stranger and more wonderful than our ancestors could have dreamed. They looked up at the night sky and saw the dome of heaven decorated with fixed stars. We look up and see galaxies racing away from us through expanding space, black holes where time itself comes to a standstill, and the afterglow of the Big Bang still warming the cosmos after nearly 14 billion years. Our descendants will surely look back at our current understanding with the same mixture of appreciation and amazement that we feel when we consider how far we have come since ancient times. They will marvel at the questions we were just beginning to ask and the frontiers we were just starting to explore. The possibility of variable light speed, which we have contemplated tonight, may seem quaint compared to the revolutionary insights that await discovery in the centuries to come. But this progression of understanding does not diminish the wonder of our current moment. If anything, it amplifies it. We are living at a time when human knowledge is expanding faster than ever before, when new technologies are revealing previously hidden aspects of reality, and when the boundaries between the possible and impossible are constantly being redrawn. The fact that we can even contemplate questions about variable light speed speaks to the remarkable journey that human consciousness has taken. From our origins as a species, that struggle to understand fire and tools, we have developed minds capable of probing the deepest structures of reality and imagining possibilities that transcend our everyday experience. This capacity for wonder and inquiry is perhaps the most precious gift that evolution has bestowed upon us. It drives us to ask questions that have no immediate practical value, to seek understanding for its own sake, and to push the boundaries of what is known into the vast territory of what might be possible. The mysteries of light, time, and space are far from being completely solved. Dark matter and dark energy still account for 95% of the universe, yet we barely understand what they are. Quantum mechanics and general relativity, our two most successful theories, remain stubbornly incompatible with each other. The nature of consciousness, the origin of life, and the possibility of other forms of intelligence in the cosmos remain largely mysterious. These unknowns are not problems to be solved quickly and forgotten, but invitations to lifelong journeys of discovery. They remind us that no matter how much we learn, there will always be new frontiers to explore, new questions to ask, and new possibilities to imagine. As we rest beneath the stars tonight, we can take comfort in knowing that the universe still holds countless secrets waiting to be uncovered. The light from distant galaxies carries messages about cosmic history that we are only beginning to decode. The quantum realm continues to reveal new phenomena that challenge our understanding of reality. The relationship between mind and matter remains one of the deepest mysteries in all of science. Perhaps somewhere in the cosmos, there are other conscious beings contemplating the same questions that fascinate us. Perhaps they have already discovered how to manipulate the speed of light, or have uncovered principles of physics that we cannot yet imagine. Perhaps they look out at their night sky and wonder, just as we do, about the deeper nature of the reality they inhabit. The search for understanding is not a solitary endeavor, but a collective human enterprise that spans generations and cultures. Each contribution, whether a groundbreaking discovery or a simple question asked by a curious child, adds to the growing edifice of knowledge that represents one of humanity's greatest achievements. The questions we have explored tonight about slower light are part of this grand tradition of inquiry. They may seem abstract and removed from daily concerns, but they represent the same impulse that drives all human creativity and discovery. The desire to understand, to explore, to push beyond the boundaries of the known and venture into uncharted territory. This impulse has given us art and music, literature and philosophy, science and technology. It has enabled us to cure diseases, explore other worlds, and peer into the quantum realm. It has allowed us to uncover the history of the universe and to contemplate our place within the vast cosmic story. As you drift towards sleep tonight, carried by the gentle rhythm of these reflections, remember that you are part of this continuing story of discovery. Every question you ask, every moment of wonder you experience, every time you look up at the night sky and feel a sense of connection to something larger than yourself, you are participating in the same quest for understanding that has driven human curiosity since the dawn of consciousness. The speed of light may be constant, or it may vary in ways we have not yet discovered. Time may flow uniformly, or it may have hidden currents and eddies that we have not yet learned to navigate. Space may be smooth and continuous, or it may be woven from threads of quantum information that dance to rhythms we cannot yet hear. Whatever the ultimate truth may be, the journey toward understanding is what gives meaning to our existence. It connects us to past generations of seekers and dreamers, and it binds us to future generations who will carry the torch of inquiry into territories we cannot yet imagine. The mysteries of light, time, and space are not finished yet. They beckon to us from the horizon of knowledge, inviting us to continue the eternal human quest for understanding. In their depths lie answers to questions we have not yet learned to ask, and revelations that will transform our understanding of what it means to exist in this strange and wonderful universe. Rest now, knowing that tomorrow will bring new opportunities for discovery, new questions to explore, and new frontiers to cross. The universe is vast and mysterious, filled with wonders beyond imagination, and the greatest adventure of all is the journey of understanding that awaits us all.